Okay, so in this part, I will demonstrate a RSA system with small primes, and so both encryption and decryption, as well as the digital signature process. First, let's see the key ideas of RSA. So we choose two prime numbers p and q. And we compute n equals to p times q, and theta n equals to p minus 1 times q minus 1. Then what we do is, we choose an exponent e that is co-prime with theta n, and compute d such that d times e equals to 1. Mm, uh, so the public key is e comma n, and it is shared with everyone since it is public. And private key is d comma n, and it is only kept secret with the owner, not it is not given out in public since it's the private key. So encryption and so let us go with the encryption and decryption flow now. In encryption flow, what happens is, person A, who is the original person who is receiving the message. So person A generates private and public keys. So since public key can be distributed to anyone, and the sender, who is B, let's say B is Bob and A is Alice. So Alice is the one who is the original receiver of the message. So Alice generates private and public keys, and Bob, who is the sender of the message, he uses the public key of Alice in order to encrypt a message to send to Alice. And he sends the message to Alice. Alice receives the message which is in garbage form since it's encrypted. And what Alice does is she decrypts the garbage message using her own private key, which is private to her only. And after decrypting using the private key, uh, Alice can read the message, which is now generated in plain text. In this way, the encryption and decryption way works, so that there is no hampering of messages in between. Similarly, in digital signature flow, what happens is there is actually key value pair of public key and private key generated, such as as same as in encryption and decryption process. So what happens is person A was person so Alice generates a RSA key pairs of private and public key. So public key is shared with Bob since it is public, and can be shared to anyone. And to sign a message, Alice generates a hash as well, and using hash functions. So Alice uses its private key to sign it, and Alice sends the message, hash, and the signature to Bob, so that Bob can get the message and hash it, and use the hash to compare the hash with Alice, so that the sender hash and the receiver hash, which is just now generated, is same. And in this way, if the two hashes are same and the signatures are same as well, not the signature, but if both the hashes are same, then it means that the message is same, which means there is no any changes in message in between, and the message that's being sent is original. In this way, the message is not like decrypted or anything, but only the hash are compared in order to know that the original text is the same. This helps to this helps in knowing that the message is valid, and it came from the sender. Actually, it actually came from the sender. Okay. So so as I already mentioned, the difference between encryption is that, in encryption the text is converted back and forth from normal to garbage and garbage to normal. In the process of digital signature, the text is hashed and the hashes are compared instead of the message. So in this way, these things work. Let's go over the pseudocode for key generation. Mm, okay. Uh, a key generation function that takes small primes p and q, and it computes n, theta n, and it picks an appropriate e and finds d using a modular inverse function. So functions encrypt underscore int and decrypt underscore int is used to handle the RSA encryption and decryption part. So functions sign int and verify int are used so that that a signature and the verification process are implemented on a small integer hash. Okay, so oh sorry, I was trying to run it. So for sample runs, I have used like three different small pairs of prime numbers. For example, like PQ equals to 11 or 13 or 17 or 19 or 23, 29. So for each pair, what I did was I generated keys and encrypt a simple numeric message on a or a short string converted to character codes and decrypted it back to show that RSA works. Then I signed the hash of a short message and verify the signature, showing that changing the message showing that changing the message causes verification to fail.